I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about multi-layer perceptron and why we should learn this multi-layer perceptron. Learning multi-layer perceptron, that we are calling it as MLP, is essential because they form the foundation of deep learning by demonstrating how artificial neurons can be organized into layers to model complex patterns in data. MLPs are capable of learning both linear and nonlinear relationships, making them suitable for tasks like classification, regression, and prediction. They help us understand critical concepts such as backpropagation, activation function, and gradient descent, which are used in more advanced neural networks. By learning MLPs, we gain both theoretical knowledge and practical skills applicable to a wide range of machine learning problems. We'll see one by one. And why multi-layer perceptron? All you know that in the previous lecture we have seen what is the limitations of single layer perceptron. In the the limitation of the single layer perceptron is it cannot solve non-linearly separable problems. Non-linearly separable problem in the sense if you are finding out is if you are marking the patterns in the plane, if you are able to separate the positive classes into negative classes, the single plane, we can use the single layer perceptron. If as far as the XOR gate is consider 00011011, we are getting the output for 001, for 11 also we are getting the output, it is equal to 0, and for these two cases we are getting output as equal to 1. If you are marking it in the plane, here the positive classes, that is zeros, are separated by the positive classes, that is 1, with the two planes. More than one planes we are using, and we are not able to classify into the positive classes with the negative classes in a single plane. So that we have to, in these type of cases, we have to go for multi-layer perceptron. This multi-layer structure perceptron consists of input, hidden layer, and output layer. Multi in the sense more than one layer we are using it. So we are using for classifying these problems into input layer, hidden layer, and output layers. So it includes hidden input, hidden, and output layers to model complex relationship. The capability of multi-layer perceptron is MLPs approximate any continuous function. The universal approximation theorem we are using it. And why we are using here the activation? In the previous case, we have used the step function as the activation function to classify the signals as output as 0 or 1. Whereas in the multi-layer perceptron, we are using the sigmoidal function as the activation function. Why we should use the sigmoidal function? In the sense, the sigmoidal activation function is widely used in neural network because of its key properties. It is smooth and differentiable, which is crucial for training models using gradient descent as it ensures stable and computable gradients. It is non-linear. It is a nonlinear nature allows neural network to learn complex curved decision boundaries instead of just linear ones. So if you are taking this is the linear, if suppose if you are having the pattern, if you are able to classify the plane is like this, non-linear or curved, we can able to use this grade sigmoidal activation function. Additionally, the output range between 0 and 1 makes it particularly useful in binary classification problems where the output need to be interpreted as the probabilities. These characteristics make sigmoid as an active choice, especially in the output layer of binary classification. The sigmoidal function, the activation function is given by sigma z is equal to 1 divided by 1 plus e power minus z. This z is the weighted sum. We have seen, no, we are able to find out x1, w1, x2 w2 x3 double x3 w3, and we are going to buy, and also you have the bias weighted sum weight input, we are going to get it, that value we are going to substitute for this z. This is the binary activation, and if you are differentiating, you are going to get this value phi of s sigma z, sigma dash z is equal to sigma z into 1 minus sigma z. It simplifies the back propagation that we will see one by one. And in the back propagation, the learning algorithm of a neural network, what is back propagation? Suppose if you are applying the pattern to the neural network, we have the input pattern, hidden layer, and it is the output layer. We are sending the set of patterns to the input layer, and input is associated or connected with the hidden layer through the weight value and also output value. My target output, I should get 1. Instead of getting, I am going to get zero point 0.5 alone. So what is the difference? 1 minus zero point 0.5. So it is an error. I need to get 1 as my target, but instead of getting, my output would be only zero point 0.5. So I found out the difference 1 minus zero point 0.5. So this we are calling it as error. In these type of cases, we are using this back propagation algorithm. What it will do is it will be sending the output back to the hidden layer to input layer. So front and forth, it will be going and back, coming back until we get 1 minus 1, that the convergence, the error is equal to 0. So the backpropagation algorithm is a supervised learning algorithm. It is used to train multi-layer neural network by minimizing the prediction error. Here, what is our ultimate aim is we wanted to minimize the error. 1 minus zero point 0.5 is zero point 0.5. Again, the second episode, we are the epoch, we are going to get 1 minus zero point 0.7. So error is zero point 0.3. Like that, till we get 0, we are going to send the output to the input to the front from back. So it adjusts the weight in the network by propagating the error from the output layer back to the input layer using the chain rule of calculus. And we'll see. So what is the chain rule? First, for forward pass inputs are passed through the network to compute the output. And error calculation, what I've said, if I'm getting only zero point 0.5, my target is 1. We are going to calculate the error. Error is computed using the loss function. This is the generalized formula. E is equal to error is equal to 1 by 2 into y minus t the whole square. Otherwise, we will write it as zero point 0.5 into y minus t the whole square. What you are getting and what is your error? That is target, you are going to get backward pass gradient of the error with respect to each weight or calculated user. This is the gradient value. We are calling it as delta is the gradient value. We are going to find out delta gradient. This is the gradient, and this is found out by y minus t. This is the target, this is what you are getting, and here sigma dash of z, sigma dash of z, that I'll tell you how we are going to get it from the sigmoidal function sigma z. Sigma z, you know that 1 divided by e power 1 minus e power minus z. From this we have to differentiate it, and we have to get that sigma dash of z. And weight update is given by, because if you are not getting the targeted output, whereas the problem means what we are going to do it in the neural network, naturally we have to update the weights. Update the weight means a change in weight we have to find out, or weight, updated weight is given by that is new weight. Updated weight we are calling it as the w new is equal to old weight minus eta into delta into input. So delta, we know the formula here, and this n- l- eta is the learning rate we are going to initialize in the while you are starting the problem into input. What input we are not going to get, and the sigmoidal function for, and before going into the problem, I'll tell you how to find out this sigma dash of z. It is a simple formula. The sigmoidal function is given by sigma z is equal to 1 divided by 1 plus e power z. So in this case, find the derivative. If you are differentiating, sigma dash of z d by dz of 1 divided by 1 plus e power z. Using the chain rule, so we are going to get a y. So I'm going to substitute sigma z is equal to y 1 divided by 1 plus. So here we are going to find out dy by dz is equal to d by dz of this value, d by dz of this value sigmoidal function. So we are going to substitute u is equal to 1 plus e power z. So in this case, dy by dz is equal to 1 by u. If you are differentiating dy by dz, we can write it as this. If you are taking d by dz, how you are going, u power minus 1 into, if you are going to differentiate u power, here u power minus 1 will be there. This we are going to write it as y is equal to u power minus 1. If you are differentiating dy by dz, u power minus 2 into du by dz. So we will write it as 1 by u square into du by dz. So now compute du by dz is equal to, what is the formula here? That du, what we are going to substitute is 1 plus. So in this case, if you are again differentiating, you are getting minus e power minus it. And substitute back, in this case, substituting, if you are substituting in this case, so we are going to, in this, we are going to get 1 by sigma z is equal to e power minus z. Here that 1 plus e power minus z the whole square. Again, if you are substituting, if you are simplifying this, we will write it as 1 divided by 1, that is sigma z is equal to 1 divided by 1 plus e power z. Otherwise 1 is equal to 1 minus sigma z is equal to e power z divided by 1 plus e power minus z. So if you are substituting all those values, this we can write it as sigma z divided by 1 plus e power z into this we can separate it 1 divided by e power 1 plus e minus z 1 plus. So this we are writing it as sigma e power z. This separately we will write it as, and if you are substituting this, we can write it as sigma z into 1 minus sigma z. So example, sigma z, if you are substitute, if you are getting, that is my error, if I am getting 675, 0.675, I am going to substitute with this. The sigma of, say, that means we are going to substitute 1 divided by 1 plus e power minus 0.675. We are going to find out, we have to use calculator and we have to find out the exponential value. Finally, we are getting sigma z. So in this way, we are going to calculate the errors. On example problem, we'll see why it is important. So the backpropagation enables neural network to learn complex patterns efficiently and is the foundation of modern deep learning. And why backpropagation for especially for XOR problems? This we can call it as, often we are call it as XOR problems. So the XOR function is not linearly separable. Why we are calling it as non-linearly separable? If you are finding out a 0 0 0 1 1 0 1 1, the output is 0. For 1 1 is output is 0. Here for this 1, for this 1. If you are able to separate zeros with the 1 classes, we need two planes. So we are not able to separate linearly. So the single layer perceptron, we cannot able to use it for solving the multi-layer that is planes. So we have, in these type of cases, we are going to use multi-layer perceptron MLPs. In order to design this network, we are going to take multi-layer in the sense input layer, hidden layer, and output layer. Here, for my input layer, I am going to take two neurons, x1, x2, two hidden neurons, h1 and h2, one output neuron y, and the sigmoidal activation functions. I am going to use it. The algorithm what we are going to update the weight is backpropagation algorithm via error gradients. The formulas we have seen, and this is the XOR gate. The truth table, two inputs x1 x2, output is given by 0 0, output is 0, 1 1, output is 0. For these two cases, the output is 1. And the network architecture is given by, as I've said, input layer, hidden layer, output layer, one neuron, hidden layer, two neurons we are going to use, and input layer also two neurons we are going to use it. Input feature we are not going to use, that is we are going to use features x1 x1, that is 0 0 0 1 1 0 1 1, XOR problem only we are going to solve it. And y is the output and t is the targeted out. Targeted out means for 0 0 I should get 0, 1 1 I should get 0, 0 1 we should get 1, and 1 0 we should get 1. Targeted output learning rate we are going to fix it, and the sigmoidal function as the activation function 1 divided by 1 plus e power minus z. This is the activation function we are going to use it. So this is the network. Here we can call it as a patterns x1 and x2 and h1 h2 and h1. This is the hidden layer. Each hidden layer is associated with one binary value, and binary values always the input value is equal to 1. Both the cases the input value pattern is 1, and here x1 is connected with w1 and w2 to h1 and h2, and x2 is connected with w3 and w4. Similarly, h1 is connected with the weight value w5, and h2 is connected with the weight value associated with the weight value w6, and this is your output. This is the simple multi-layer perceptron. And in this case, we are going to take on a pattern 0 0 0 1 1 0 1 1. And this case, I am going to take this pattern 1 1. And whether I am getting the output, what is the targeted output? 1, for this also 1, for this also 0. So for this also 0, for this 0. So here we are going to take this pattern 1 0, and the targeted output is 1. And in this case, what we should do is, first step is we have to initialize the weight. So the input to hidden layers, input to hidden layers, what are all the weights we are going to use it in this case? In this case we are using w1 w2, and from x2 w3 w4, from h1 to output w5 and w6. This we should remember ever. So we are initializing the weight w1 is equal to, that means x1 to h1, x2 to point 2, point 1, point 2, point 3, point 4, x1 to h2. So x1 to h2 in this case, x1 to so we are going to just point 1, point 2, point 3, point 4 we are going to assume it, and the output layer values 0.5. For our understanding easily, we are going to take any values we are going to assign it. And bias values, bias bh1 here 0.1 in this case, here 0.1, 0.1, and this value, bias value we are going to take, bias value 0.1, b naught. So the learning rate we are going to assume a eta is equal to 0.5. So we are going to forward bias. We should compute the hidden layer input and output. What is the formula? As I have said, one neuron is connected with the two neurons. This is x1 if you are taking here w1. In this, and another one more value w2 if it is connected, we are going to use it. This is x1, h1 and h2. Similarly, another neuron, it should be connected with all the hidden layers. Z1 is given by x1 w1 plus x2 w2, x2 w2 here, plus this first neuron alone, plus this bh1. These values we have to, what is the pattern we have to, we have taken x1 is equal to 1 and x2 is equal to 0. So 1 into 0 1 or 0 into 0.2, and here don't confuse with it, plus 0.1, the output input is always 1, 1 into 0.1. If you are multiplying and adding, we are getting 0.2. Similarly, in after finding out h1 weighted sum, we are going to, we have got 0.2. And how we are going to get the output for this neuron? We have to use the sigmoidal activation function 1 plus e power minus z is equal to 1 divided by 1 plus e power minus uh, 0.2. If you are finding out a sigmoidal function, we are going to get 0.5498. Similarly, for h2, how we are going to calculate x2? Here x2 into, that is x1, x2 into this value w3 In this, what is the value? It is coming x2 into x1 into w3 and x2 into w4 plus bh2. If you are substituting all the values, we are going to get 0.4, and after applying the sigmoidal function e to the power zero point 0.4, we are getting 0.597. And these two hidden layers, now it is having the value 0.59, that is 5498, and another hidden layer is having 5987. These values we are going to again find out. This Z3 H1W5 H2W6 plus B0. This value we have taken 0.5, this value we have taken, and these values we have to multiply plus into 1.1. In this case 0.7341. So we have to weighted sum of the output, and we have values 1 divided by 1 plus e power 0.7341. So if you are finding out, we are going to get 0.6751. What is the output we have to get for this pattern? Our target output is naturally is equal to 1, but what here we are getting 0.6751. So the error is 1 divided by 0.6751. Mm. So we have to compute the error. Target is 1 and output we are going to get 6751. The error formula is given by 1 half into y minus, that is t minus y, the whole square. So 1 by 2, target 1 minus 0.6751 whole square. If we are subtracting and taking square, we are going to get 0.0527. What we are going to do is input layer, hidden layer, and here the output, and output we got the error will be sent back to the hidden layer and input layer. Still we get the zero error. So the output layer, we have to compute the backward pass. Compute this delta for output neuron. Use the formula del z is equal to sigma z into 1 minus sigma z. This formula we have seen, and the del output is given by y minus t into sigma dash of z3. 6751 minus 1 into 6751. That is, if you are multiplying and dividing, we are for this we got value sigma z into 1 minus sigma z. We derived the formula, and substituting we are getting minus this value. Again this value should be sent to where? Sent to the hidden layer h1 and h2. We are sending back whatever we found out. This we are getting these type of values we are going to get, and and update the hidden where weights from the hidden, update weight from the hidden to output. The formula is given by w5 eta into del output into h1. Point 0.5 we have taken, w5 into eta point 0.5 we have taken, and the output what we found out here, and this value we are going to take and substitute, and then h1 into h1 value we found out already 1 minus h1. This we got it. Similarly for the hidden layer 2 we got 0.013, and in this case if you are substituting all those values, we are going to get 0.6213. And also we have to update the value for bias. The formula only thing is b naught we have to take instead of w eta and del output. We are substituting, we are getting 0.1356. So similarly update the weight from the input, that is in hidden, from hidden to input. So we are the same formula we are applying. Instead of output, we are going to take x1 and x2 and 1 0, we are getting this. Similarly w3 and w4, all the weight we have to update it. And bh1 also bh2 we are getting 0.011044 and 0.1052 we are getting. Hope everyone understood the step for weight updation. So in this way, if you are finding out for all those values, this is your old weight, we have fixed it, and new weight we have got it. By keeping this value again, we have to apply the patterns. If you are applying the patterns, repeat for all input values. For t is equal to 0, in this case for this case t is equal to 1, t is equal to 0. For several epochs, the network gradually learns the correct output, means it has to converge. 0 means 0 minus 0, we have to get 1 minus 1, we have to get. After finding out all the values, again and again we have to find out, and again feed forward pass we have to do it. If we are getting error, feedback pass we have to do it till we get 0, that is error. So in this way, it will be using us to calculate the error value and find out the original output. So finally coming into the conclusion, backpropagation uses the chain rule of calculus to propagate error backward and upward weights. And the sigmoidal activation function ensures the smooth derivations, and the training continues until the error continues. Targeted output is 1 means my output also, after finding out all the new weight values, and again if I am applying the patterns, I should get output is equal to 1, and if I am subtracting y minus t is equal to 1. This we are calling it as the convergence in the sense 0 error. So until we get 0 error, we are sending backward and forward and backward by using the backpropagation algorithm. So in this way, the backpropagation algorithms is used to find out the output in the multi-layer perceptron. Hope everyone understood the basic concepts about this backpropagation. The remaining things we'll discuss in detail in the next lecture. Thank you.